record. Then here. Can you see my screen, right?
Yes.
Canvas. Courses. 4300. Announcement.
It's the top one, right? The group projects one.
I think so. Yes, it is. Here. Okay, your question. Fine.
So these are the topics that we're given to be able to do, right?
Or whatever you like.
I think our group was group B, and we wanted to make processing on a Raspberry Pi 4, capturing images and then transmitting it encrypted back to a main server.
Wow. Okay.
And then we would test efficiency of different encryption algorithms for doing so.
I love that.
Can we do that?
Please do that. That's basically what I want. That's very cool.
Okay. Thank you.
You're most welcome. Anybody else? Oh, so, Christopher, don't forget, we're going to look to all the performance evaluation metrics, right? We're going to look to the CPI, execution time, elapsed time, right? And also we're going to look into how much power.
Absolutely, Professor. I don't have a good way to calculate power consumption.
I'll show you. One second. That's why I brought it with me somewhere here. One second. Where did I brought it? Here. Hopefully I didn't drop it on the ground while I was walking. Oh, here. Can you see in my camera?
Yeah.
So this is actually what a Bluetooth USB power tracker that will be connected to your computer or whatever. And once you will just put it into the Raspberry Pi USB, right? It will start telling you while the Raspberry Pi is running how much power you are consuming.
Does it put it out as a graph, or does it just put it out as raw data?
It can give you a graph.
Okay. How much is that?
$20 or something, 25 bucks on Amazon.
Okay. Thank you, Professor.
You're most welcome. Okay, now, other people, do you have any question? Hello?
I think not as of right now, Professor.
Okay. The rest of you guys, do you have any question, any concern? There is no question, right? So I can stop sharing this, and then I will start talking today about what the continuation and wrapping up last chapter 1, which is basically we're going to talk today about what Amdahl's law, right? So everybody can see my screen, right? Can you see what is presented on the screen?
Yes, Professor.
Okay, so for Amdahl's law, so do you guys remember we said, performance evaluation, we look into the whole entire performance, but now, this law have been made to identify where exactly the parts in the system need to be accelerated, or it need modification or limitation. And then, when you will alter this part, that will tell you by the end how much performance you gain or you lost. So Amdahl's law is used for performance improvement from speeding up as a part of the computer. Let's say that, I found out that, I would like to change my memory to a higher version, or, change my memory technology from DDR3 to DDR4. That will be a very good add for my system. But, by how much it will add to my system in terms of performance. So Amdahl's law will help us to do that. So you're looking into what speed up. To calculate the speed up, it's basically the execution time for the whole entire task without enhancement. That means your computer without changing anything, right? Divided by the entire execution time for entire task using the enhancement, which is altering the memory or altering the processor, or changing your motherboard, or so on. And of course, do you guys remember when we said the performance is 1 over the execution time? Do you remember this equation? So if you would like to calculate the speed up by performance, you will flip, right? So that's why, performance for entire task using enhancement over the performance of the entire task without enhancement. There is other way you can write it, which is basically the execution time after improvement is equivalent to the what? The execution time without any affection happening into the system plus the ratio between the affected amount of the improvement. Let's have examples. So suppose a program runs in 100 seconds on your machine, okay? Interesting. No, it's sorry about that, guys. Anyway, suppose that your program is running in 100 seconds on your machine. With what multiplier responsible, that means, there is a circuit or, computing element doing multiplication, which is taken out of this 80 seconds. So 100 seconds, the whole program, we figure out that, the multiplication in that task or the program is 80 seconds. How much do we have to improve the speed of the multiplication if we want the program to run 4 times faster? So in this case, we're going to use this 4, right? We said that we need to improve the program how many times? 4 times, right? Currently is 100, right? We need it to be improved 4 times. That means, the total it should be how many seconds? 100 divided by 4, which is 25 seconds, which is what? Execution time after improvement equal what? Execution time unaffected. Unaffected, we know that out of the 100 seconds, there is 20 seconds. There is no relation between the multiplication and it, right? So that means, 100 minus 80 is equal 20. So this is a 20. Do you guys agree? Then plus the ratio of what? The execution time affected divided by amount of time you would like to improve, right? So the time affected is 80. And I'm not sure what is the speed up will happen in this case when I would like to reach this amount of time. Make sense? Hello?
Sorry, Professor, I'm kind of lost. Could you explain it one more time?
Again, my computer running a program and it's taking 100 seconds. So far, so good? I figure out that, the multiplication circuit or computing element inside my processor out of this 100 seconds is taking 80 seconds. So far, so good?
Yes.
Okay. So 100 minus 80 is what?
20.
So this 20 seconds doesn't have any relation with multiplication. Do you agree?
Yes.
Okay. Now my question, how much do we have to improve the speed of the multiplication? So we need to improve the multiplication, right? If we, how much are we going to improve it if we want the program to run 4 times faster? What program? The whole entire program, right?
Mm-hmm.
Okay, in that case, I know that my program is 100 seconds, right? If I improve it 4 times. That means it's gonna be 4 times faster. That means it should be running in how many seconds?
25.
Exactly. So he was 25. But I know before that 100, it has 20 seconds, doesn't have any relation with what multiplication, right?
Mm-hmm.
So here is the 20 second. Plus what? I remember that, the multiplication used to take 80, right?
Mm-hmm.
It's 80. How much I have to put here to make this equation equal 25? That will be the speed up of the multiplication I added.
Okay.
Make sense?
Makes sense.
Okay. So in that case, you do what? You calculate it, right? So gonna be 25 minus 20, right? So 5 equal 80 divided by speed. So in this case, speed is equal 80 divided by 5, right? So 80 divided by 5 is what? 1. Then you already have 40,
6.
8, right? So that means, this multiplication, instead of 80, it has to be running what? 18 seconds.
Shouldn't it be 16, Professor?
Is it 16?
Go to 18, it'd be 90.
Wait, it seems that I forgot my math. 80 divided by 5, right? 16, you're right. I'm sorry. Right? So in that case, instead of running 80 anymore, it has to be running what? In a way that it will be what? 60.
18 second.
Huh?
Yes, 18 second.
Okay, perfect. Now, Hennessy and Patterson, because sometimes people use stuff wrong, right? And do you remember when I told you the benchmarking, if you use the small benchmarks, it might be misused and people will start giving wrong conclusions, right? So that's why, they put in the last of every chapter, set of pitfalls and, enhancements. So the pitfalls of Amdahl's law, there is no way for you to come and say that I would like to run my computer in 0 seconds, right? Or, it is impossible for you to do some improvements. So that's actually the pitfall, right? So for instance, this equation in front of you is basically whatever we wrote here, right? In this line. So I put it here. And I'm looking for example that it will be misused, the Amdahl's law, right? So for instance, the example of the multiplication account is 80 seconds out of 100 seconds, right? How much improvement in multiplication performance to get 5 times overall? What does it mean? When I said here 5 times, that means what? 100 divided by 5. Do you agree?
Yes.
In that case, it's going to be what?
20.
20. And the 20 as it is, right?
Mm-hmm.
Yeah, the 80 minus 100, right? 100 minus,
Yeah.
right? So now it's 80 divided by n. I have a question for you. What is n it will be?
N should be the speed, right?
Yeah, n now gonna be what?
0.
0. Gonna be 0 equal 80 divided by what? N. So n is equal 80 divided by what? 0.
Yeah.
What does it mean?
The universe gonna break.
I mean, nothing will happen. That's why it's
Yeah.
called what? Pitfall. So, everything has a limitation. Even, when I told you there is a law have been made in 60s and 70s, it's called Moore's law, which is basically predicting that every year number of transistors on the chip will be doubled, right? This law will actually what currently is not actually running as it should be. It's not two times per year due to the, the getting close to that, we will not have any electrons between the source and drain. So the semiconductor will actually collapse. So every single law that we made in the science, right, or in general in science, it's questioned. What does that mean? Question that mean it might not work forever. Who knows? Maybe Ohm's law, right? You remember Ohm's law was the current and volt, and you already have the relation. Maybe in a certain level will not be linear, right? Which is correct. I will give you example, right? So do you remember the Ohm's law, right? IV And then you do like this, right? Do you remember that?
Yes, I remember.
Yeah, because you know V is equal I times R, right? So that means V and I have this relation, right? But
Mhm.
this is actually not forever, right? Because you know, if you change the pressure and temperature on the resistors, what will happen? You might get like this. You might get like that. So non-linearity will happen. So you have to know that every single law in the world is questioned. Maybe it will not work forever, right? That's basically what I'm trying to tell you in this slide. Okay.
I see.
Now, to calculate the overall speed up, not the speed of a certain unit we change. So there is an equation, it's called overall speed up. This equation is equal what? 1 over 1 minus f plus f divided by the speed. What is f? Is the fraction of the enhancement that I received, and s is the speed up of the enhancement of this specific fraction. So overall of my system, the whole system, it has memory, it has CPU, it has hard drive, it has you know, the microphone connected to USB, it have whatever, right? So you already have what? 1 over 1 minus f plus f divided by s. F in a fraction enhanced, s is the speed up of the enhanced fraction, right? So look at this overall speed up. This is a question, right? Overall speed up, I need to calculate it. If we make 90% of the program 10 times faster than before, I would like to calculate the overall speed up if I succeeded on making 90% of the program run 10 times what? Faster. So in that case, you know, I would like to use this information I have to fill into this equation, right? So now we know what is my fraction of enhancement? 90%, 0.9, right? What is the speed up? It's 10 times faster. Then, you know, I calculate it's going to be 1 over 1 minus 0.9 plus, you know, 0.9 divided by 10. The total all of the overall speed up is 5.26. It doesn't have any what unit, just a number. It's a number to indicate how much I speed up. So you cannot see here second or something, you know, just like a speed up. Okay.
I see.
Another question. Overall speed up, if we make 80% of the program run 20 times faster. Overall of speed up, we make for 80% of the program to run 20%. Now, what is the fraction? 80%, 0.8. Now, wait a second here. Of a program run 20 times faster, not 10 times, 20 times in percentage. In that case, we are talking about what? Over 100, there is 20, right? So gonna be what? 120. So which is what? 1.2. So then, you know, in your overall speed up one, yes.
Can you repeat me that 1.2? I still lost that one.
A program run 20 times faster.
Yes.
Program run what? 20 times faster. That means, you know, if it's running now, it's 100%. Do you agree?
Yeah.
20 times added into the 100%, what is the value will be?
120.
Exact, divided by 100.
1.2. Okay, let's see.
Yeah, $5, please. Okay. Anyway, so overall speed up in this case, you put the equation, right? 1 minus 0.8 plus 0.8 divided by 1.2. So the speed up I succeed in getting it is 1.153. Of course, if the number of the speed up go up, that means, you know, you succeeded to significantly improve the total performance. Do you agree? Sounds good to everybody?
Sounds good.
Okay. So far, so good. Any question? Anthony, do you have any question? Christopher, everything's okay to everybody?
Everything sounds good, Professor.
Super. Now I'm gonna show you a real case scenario on my research, about Amdahl's law, right? I will tell you a really nice story, but the story is in this part. This is one of my papers. But before the papers, here is some information about a process processing some computation elements. So for instance, looking into number of processors I have on the chip, right? And looking in how much speed up I might have in a certain application, okay? And looking into the parallel portion, right? Do you remember when I told you some of the algorithms can be running in parallel fashion, while some of them, unfortunately, it has to be sequential behavior. And we had some example before in the last lecture, if you remember. If you don't remember, let me know so I can repeat. You guys remember that?
I can't say that I have, Professor. Do you think you can just remind us?
Sure. So, do you remember when I told you that, when we build a processor, right? We, architect people, they look at hardware and software. Do you agree? They make everything almost parallel. But end of the day, this type of chips and processors running what? Algorithms. Do you agree?
Yeah.
Some of the algorithms by nature, it's sequential, right? That means, A plus B, it has to be C. Then I have to use C to be added to D, it bringing F. Then F, it has to be added to whatever to bring Z. So end of the day, you cannot jump to F without adding all of those, right?
Yeah.
So that's sequential behavior. So there is a level of architect people who architect the application, which you are, guys. You guys now, with this course, will be able, instead of somebody giving you homework and say that, Philip, go ahead and implement for me this algorithm using C code, C language, right? Before you just write the code because you are looking for the right answer. Do you agree?
Yeah.
And then, I'm going to get the degree. I finished my quiz. Now, this course is changing your way of thinking. Instead of just writing the code to get the answer, no, you have to write it with a strategy to get the best performance while you're delivering the answer. Make sense?
Yeah.
Exactly. So you will look into the algorithm like this. And based on looking to the algorithm, you'll figure out where parts in this algorithm need to be parallelized. Can running like in multi-threads, for instance, right?
Okay.
While I know that some of them, unfortunately, has to pass to each other. That's why there will be a common memory. They call it queue, right? So they push data into the memory that it will be used, share data, move in, and you move forward.
Okay,
Of course,
yeah.
Intel and all of the chip makers love everything to be in parallel, right? But sometimes relations between variables tend to be sequential. Somebody can give me an example of sequential algorithm. Do you have any in mind an algorithm that's running in sequential behavior? I can give you example. Encryption. Do you know that in encryption, people work in security in encryption and decryption and stuff like an algorithm like hash function, the SHA-1, and I give it to you, right? It's purely sequential. But there is a level of parallelism you can apply it because the belief in crypto that when you add the sequentialism, that you will increase the diversity between bits inside the design, that will increase your security margin. So it will make it more difficult for the hacker to reverse computing and figure out what was the key or what was the message he tried to hide and so on. So one of the most famous branch of science, crypto. Yes, Christopher, you want to say something?
Well, I was just saying FPGA boards are very common to make parallel processing things. But yesterday, I was actually helping someone program, I think, the elephant encryption algorithm on an FPGA board.
Yes.
Someone had asked me for help, and it was the first time I had seen that one, but everything was a very sequential step in order to create the mask.
That's why I added in the list. Have you seen it?
Yes.
There are 10 elephants Romulus, Ascan, Ziodik, Tiny Jambu. There is Gauge. I was working with Air Force with it. There's a couple of them. You will see a lot of sequential stuff. You know what I mean? But post-quantum, some of it is running in parallel. Post-quantum crypto. That's a different story. Okay. And actually, I'm making some security protocol using post-quantum, and it's gonna be a new US patent. So if anybody would like to join, tell me. Okay. Anyway, back to the future. So if you look into it here, you will think that, if I keep adding processors, I will keep getting better performance, right? Amdals will come and tell you that's not true. You keep increasing the performance, yes, but after a certain point, you reach what? Saturation. Do you agree?
Yes.
And here's the saturation. So if you have 256 processor actively running in the chip doing what you want, it will be equal to this big number of processor running on the chip. But of course, consequence in this case, your power will be consuming more, right? So looking for the turning point that I don't want more processor to be active, turn them off using the power management. That will be a very good strategy for you to get better performance, and the battery lifetime will be extended, right? So you will not be running out of juice fast, right? Same thing happened here while I was working for a project for NSF, National Science Foundation. We were trying to accelerate JTK, which is a DNA sequencing tool have been developed by Stanford. And this tool, the idea, they take your blood drops, right? They put it in a device, and that device will creates an image of your all DNA genomes and DNA bases. And DNA, you guys know DNA, right?
Yes, Professor.
So in DNA, we know in binary we are 0 and 1, but DNA is based on 4 bases of carbons. It's basically GTCA. Those 4, with combination of them, you will start building genomes. And based on these genomes, they will start cluster to build proteins. And when you build proteins, you start building, the color of your eyes, the proteins will build your liver, kidney, and so on. Then you will be constructed. So imagine the human body like that. So end of the day, you are no longer 0 and 1. You are GTCA, right? Which you can actually move it into a number system 4, right? So you can be like 0, 1, 2, 3. You can put A like this, C like this, T like this, and G. And then you can just build down a system for looking into the gene that can cause, for instance, cancer. For instance, the gene that can cause, people lose their hair fast, and so on. So that JTK tool was doing this. But, JTK tools, when we were running it, it was taking days and days in supercomputers. So we use FPGA, Christopher. We use FPGA with learning all of the possible parallelism we can have in FPGA on cloud. And we came into a conclusion. Look at this, the conclusion. In the conclusion, if we keep increasing number of processor, we found out that, up to 35, we are almost like, running GPU, but on FPGA. So we build this number of processors on FPGA, and we succeed to reach the point of if GPU is running and doing this job. But the good thing, FPGA, it was less power than GPU, which is very important for the green energy concept. And who helped us? Amdahl's law, right? Makes sense to everybody?
Makes sense.
Yes.
Okay. Now, there are different performance metrics Hennessy and Patterson stressed on them that can be regularly used based on the the nature of the data, the format of the data. And everybody knows that the data can be integer or it can be what? Associated with fraction, which is basically they call it real number, right? So if I would like to dedicate a performance about how many instructions per certain amount of time is running in integer format, I use MIPS, which is not the microprocessor we're going to study. MIPS in this case is a matrix, stand for million of instructions per second. How many millions of instructions per second I'm executing for data integer format. So MIPS as an equation is a number of count of instruction divided by execution time of this times 10 power 6, because we are looking for million instructions, right? You can change the musical chairs, right? So, execution time, if you don't have it, you already have the clock rate, then you flip it, it's going to be clock rate, right? You have the CPI, then you can go into the CPI and so on, as we did with the previous definitions of the execution time. Do you guys remember that, right? So in that case, so you can write it like this, or, if you don't have it directly, you can write a clock rate divided by CPI times 10 power 6, or you can write the CPI, in this case, is that instructions of count times CPI divided by clock rate, whatever you have. Why we need it? So we can look into the dependencies and we can look where is the bottlenecks of the execution. It is also this case, because if you remember, the instruction going into the chip end of the day is a machine language, right? So who is actually causing the number of instruction to be by these numbers? It's the compiler technology. Maybe the GCC version is not really good enough in front of the Python 3.8 or 3.7, or maybe GCC 8, it will be more optimized than GCC 7, or so on. So the number of instruction will be different. Then the footprint on the memory will be different. That's something you need to put in your consideration, right? Also, the way that the programmer as a developer wrote the program, right? Maybe he wrote some redundancy in his code. We don't need it. That will cause number of instruction to be exponentially or linearly extended or, descendant. Okay, definitely, there is intuition, which might be wrong, that, higher is better, which is not correct. It's not correct all the time. That's why you have to know that the relativity theorem is valid, because, nothing is fixed. Something to add with you guys, I was watching, that's not related to the topic, but I will need to tell you. You guys know that, the Earth is moving all the time, right?
Really, no?
Yeah, and you know that, we are moving with the speed of the Earth, right? So in reality, while I'm sitting now, I'm not sitting, right? So that means everything is moving, right? Though this is just like information, for fun, scientific information. Somebody was talking, a professor from NASA yesterday, and he was talking about what will happen if the Earth stopped in 1 second. Would you imagine what will happen?
Chaos.
Well, on one side of the Earth, people would be flattened, and on the other side of the Earth, people would go flying off, depending on the tangent of the spin.
Exactly.
Is it due to inertia?
Yeah, you will imagine yourself, you will be, and by the way, you would be flying with the speed of the Earth before it was stopping. You would be like, pew. You will find yourself out of the atmosphere, right?
But I like the idea that the Earth is moving relative to the sun and other observers outside of the Earth. But if you're on the Earth isn't moving.
Correct.
Because relative to you, it's not. Everything is relative.
Everything. That's basically what I'm trying to tell you. Don't take everything as a fact. The facts can be changed, right? That's why, Hennessy and Patterson in their book, they write everything and they will come and start questioning you. Do you think this is valid forever? No, because, this and this and this, right? And so on. So the way they wrote their books is really clever. And then, do you know that those guys already got like a couple of awards from the top organization, almost like Nobel Prize. Nobel Prize more into basic science, right? Those guys take like awards in architecture and computer architecture, which is like, if you take it, you're done. You can retire if you want. Your name is like almost like Einstein, stay forever, Oh, one thing also to tell you guys, My background is, kind of language is not English. It's basically German for my PhD because I used to live in Norway. So we don't say Einstein like you in English. We say Einstein. Okay, so sometimes when you hear me, sometimes I use some German words in the middle. Okay. Anyway, there is another format of metrics. It's not related to what? It's not related to integer. It's called it's mimicking and observing an instruction dedicated for what? Real number. And real number in IEEE standard that we're gonna study in chapter 3 represented with something is called what? Precision. So you already have single precision, floating point they call, double precision, floating point, extended precision, floating point, or custom precision, floating point. It depends on what is your final goal on the customized chip. So floating, that's why they put it M flops, okay, which is million of floating point operation per second, which is the same story I mentioned here, but instead of instructions dedicated for integer, it will be an instruction dedicated for what? For real numbers. And of course, a different machine has different implementation version of the floating point operations. And of course, completely different, it's completely different. Like adder in floating point is not simple as adder in the integer and so on. One of the things I need to mention, imagine that I will write you a question, say that, I have a program and this program running X integer instructions. What is the M flops? What will be your answer? Should I repeat it? Hello? Okay, again, I'm gonna give you a program. I might ask you to write a program because chapter 2, we're gonna go in assembly and so on. Or I give you the program and I give you the instruction. And I tell you this instruction for what? For integer format. And I ask you calculate for me M flops. What will be the value? 0. Thank you. That's basically, the way I like tricks. So sometimes I give you something, you need to think about what's the format of the data. Based on that, you will figure out that you don't even need to look to any information. You just put it 0. Or I can flip it. I can tell you, running how many floating point and ask you to calculate MIPS. 0, right? For those people who are really interested in technology, that when they start introducing a new chip in Intel press conference or IBM or whatever, right? And even I'm sure that Christopher for M1 when they already made it, right? They will tell you based on the benchmarks, our chip can run this teraflops per second. Have you seen that, right?
I have not.
Oh, look at it. I will send you guys link of this. So they will tell you, oh, my processor, AMD, Razer, whatever, is running 100 teraflops. So instead of M flops, millions, teraflops, gigaflops. You know what I mean? So flops here is very important because you are showing that your processor is very freaking fast that it can finish big number of instructions per second. And of course, maximum frequency is very important player, which is if you look in a reverse engineering matter, you will find that the critical path is the problem. If you go more analysis, combinational circuit is a problem. And then if you look more in a reverse fashion, you will find 2300 course was the most important course you took as a computer engineer if you are a computer engineer. That makes sense? So we are concluding now chapter 1. So we finished chapter 1, and we need to talk about some information about what we are learned so far. We talked about cost versus performance and how can we look into improving, and we can feel it based on the technology. and based on a strategy for implementing algorithm up to the whole entire stack, throwing the software, technology of the software until you will reach into the bunch of 1 and 0 switches on the chip. You will look into the hardware software hierarchy. You will look also into the architecture, whether it's going to be RISC or CISC, what the difference between RISC and CISC, what is the difference between Newman versus the other one, which is basically Harvard architectures, and which one is used in what level of application. We'll look also into the execution time as the best performance measure, and we broke it into the CPU execution time and elapsed time, which is looking into the whole entire system execution time. We'll look also in the power, and as a matter of fact, power is very important. That's why I'm not sure also you guys heard about that Russia is building, their scientists building portable nuclear batteries that can last 100 years. But I don't think, security will be, security measures and safety will pass such a kind of thing in US because a ton of incidents happen with nuclear, especially if you guys also followed that, have you guys heard about virus in computers called Chernobyl, right?
Yes.
What is this? Most of virus in computers, they just like destroy your file system or, destroy your operating system. This one is really, really, really harmful. This one, when the time of the incident happened, of the explosion happened in the Chernobyl nuclear reactor, guess what happened? He put something which will play with the voltage and the current regulator on your motherboard that will even fry your board, which is a generation of people now think about the new viruses you can make that will physically harm your board. That's why there is a branch of science now called cyber physical systems. Do you have any questions so far? Any question? No question? Okay, now I'm gonna start sharing with you the set of slides, which are gonna be some practices for what we already learned. And on the top of that, I will send to you guys through the announcement list of questions from chapter 1, like a list of problem to solve. And I will give you a 1 week from today, right? So Wednesday, you will send me your submissions of the answers under your GitHub repo. You remember the GitHub that we made for the groups? Hello? Can you guys hear me? Yes. So there you're gonna go into the GitHub, and you will have like a folder called homework, and under that folder, every single member of the group will have his own folder under his name, and he will post his homework there. Then midnight of coming Wednesday, I will post the answer to you guys on the announcement. There is no grade on the homework, but I would recommend you to go and solve the homework, because that will give you the taste of how the quiz will be look like. Make sense? Sounds good to everybody?
Sounds good.
Sounds great, Professor.
Perfect. Now we're gonna go into the Google Drive and try the 4300 and number 3. This actually talking about chapter 2. Okay, so I'm gonna be talking more about chapter 2, which is introductory of the MEPS architecture. So I would recommend, I will go through like one or two, and do you guys like me to start the subjects for the chapter 2 today, or do you like to move it to the next week? It's up to you.
Yeah, we can move it to next week.
I'm fine with that because it's better for you. You guys will be in person next week, right?
Yes.
Yes, Professor.
Okay.
Liz?
I will push it for next week, so I will not add too much pressure on you. So your head will be cleared. Sounds good. So we can finish for today, but at least you understand what I'm trying to say. Fully understand chapter 1. It looks easy, looks very easy, but watch out. There are some tricks, and believe me, from since 2018, since I'm here in Cal Poly till now, I noticed some people made really some mistakes in easy stuff. I used to do also mistakes in easy stuff, which is normal. We are humans, so we make mistakes. So that's why read the question very well, read it multiple times, triple times, and then go ahead and start answering. Also, don't forget, over only speed up in Amdahl's law is a very easy equation. 1 over 1 minus f plus f divided by s. See, easy, right? Because some people will give me answer like this. Look, 1 over 1 minus f times f divided by s. And they will lose a point. And I really hate you guys to lose points. I like you guys, all of you, to get A. Make sense? Okay?
And Professor, the one you want us to answer the question, you're going to send us by tonight or tomorrow, even just.
Tonight, basically, I teach until 8 o'clock or something like that. So normally you will find do you remember in modules, right? Under modules, I will post the video recorded version of this lecture, right? On the week 3, right? Then I will write announcement, say that, hey, folk, the homework is like this, and your due is like this. And, I will post the answer in that time.
Okay, thank you, Professor.
Sounds good. I don't want to give you the answer immediately. It's better for you to also do your work, and then I will give you answers.
Okay, so it's cool. Thank you.
Okay. Any question for you guys? Any hesitation?
Wait. Did you just say we have homework due tonight, Professor?
No. Tonight I will give you the homework.
Oh, okay. You scared me for a second because
it's cool, No. The homework is gonna be next week. You'll give it to me. So today is Wednesday, right? So your due is Wednesday. I give normally 1 week. Because I know you guys taking other courses.
Thank you, Professor.
You are most welcome. Any other questions? Any concern? Anything I need to repeat about chapter 1? I'm here.
Oh, Professor, this is gonna be more of a question when we get back. Are you still gonna be recording some of your lectures or like the slides of what you go over?
Do you guys like that?
Yeah,
I think it's helpful. Yeah.
It's nice to
I
be able
think
to
it's
review afterwards.
It's
I have a
helpful
good
and
idea.
also-
I have a good idea. I will do my best to record it while we are there.
That sounds
Okay.
amazing.
Yeah, I think that's also because if anybody ends up like getting sick, then they're able to stay home
that's
too.
okay. That's
Yeah.
okay, because this, we are not clear still from this story of pandemic, I don't know. Right? So don't worry. I will do my best. And also, I share the slides by itself, right?
Yeah.
So you will have
That's
everything.
whatever.
And if you want, my writing on the slides, I can give it to you. That's fine.
Okay.
Okay.
Thank you, Professor.
But I believe for office hours, I think the department will recommend office hours to be online. Did you guys hear that, right?
Yeah, other teachers already said that.
Yeah, I mean for your safety also, because don't forget, right? All of you guys coming to the office, right? And then some of you guys are in hurry to go for the other class and so on. So we will not be sure that the social distancing can happen, right? Let's see. Hopefully, everything will be okay and everybody will be safe, right?
See you on Monday, Professor.
See you guys. God bless you. Okay, take care. And if you don't have any question, we finished for today. If you have any questions, I'm here to help. Okay. Have a wonderful weekend.
You too, Professor. Thank you so much. How wonderful.
God bless you. Don't forget, next week on Monday, you're gonna give me a presentation, right?
Yeah.
About what? About the projects, right? Do you remember that?
Now we do.
Okay, God bless you guys. Thank you.
Professor,
See you, Professor.
Thank you, Professor. Have a good day.
that's a quick question.
Mhm.
Yeah, so right now you were saying that we're gonna give you a presentation